So one of the most important identities that pops up in trig is the Pythagorean identity. And it, as we know, is cosine square theta plus sine square theta equal to 1. Okay, and of course, this is an identity. It doesn't matter what theta is. Theta could be any real number. Okay, and again, if for some reason the the video lags, please let me know. Sometimes this thing lags a little bit. All right. Okay, there we go. Okay, so yeah, that is the identity we're going to be using a lot. Now look at problem 2 in the handout that you're told that. So I'll be doing problem 2A and I leave 2B, C, and D for you to do in your group, right? So 2A says that you have an angle where cosine of the angle A is equal to negative 8/17, and you're told that angle A is in quadrant, well, it's between pi and 3 pi over 2. So A is in pi and 3 pi over 2. That would be quadrant 3, right? And we are told that angle, I can actually draw this for you. Okay, so here is the location for angle A, that quadrant. And we have another angle whose cosine is equal to negative 3/5. Okay, and you're told that B is in quadrant also 3. Okay, and of course this makes sense because in quadrant 3 cosine is negative, right? Yeah. All right, so now there's a question about the sum of the trig ratio of the sum of those angles, like sine of A plus B. All right, now we don't know exactly where A plus B is, right? So A and B could be small enough so that when you add them, they still fall in quadrant 1, or big enough that when you add them, they fall in quadrant, like let's say A plus B might fall in quadrant 4. But we don't know that, all right? So you're asked to find the sine of A plus B. Okay? Yeah. Things that you can't do is just, let's say, add these, right? So if somebody said, find cosine of A plus B, question number B, you're not going to add these. We don't want to do stuff like that. Again, we don't know what A plus B is exactly, but we just want to find its sign. So here you have the sign of a sum. Sign of a sum. I hope you remember your sum identities from pre-calculus. That is equal to sine of A cosine B plus sine B cosine A. Okay, this identity is very important in calculus 2. The reason that this identity is important is because here you have a product. We have a product. And what you can do is you learn that you can write a product as a sum. Okay? So you can go from a product to actually a single term like that, sine of a plus b. You'll see that in calculus 2. A single term here is much easier than a product. One factor, two factors, right? One factor is a lot easier than two factors anyway. Let me not go off track. All right, so to answer this question, so here we have cosine of b. That's right here. I need, let's say, sine of a. I don't have sine of a, I have cosine a instead. All right, so what you need to do is use this identity that relates sine to cosine to find sine of a. We have cosine a, we can find sine of a. So to find sine a, use cosine square a plus sine square a equal to 1. All right, plug cosine a in there, you're going to get, so I have this cosine a. Cosine a is negative 8/17. Okay, so square that, plus the unknown is sine square a equal to 1. All right, so we're going to solve for sine a. Square that 8/17. 8 squared is 64, and 17 squared here is 289, plus sine square a equal to 1. Okay, move that 64 over 289 over. You're going to get 225 over 289. Yeah. So the thing with this equation is that you have a square equation. You need to take the square root, and when you take the square root, you have to use the root property, which says that sine of a, or absolute value of sine a, is going to be the root of that, meaning that there are two solutions. Yeah. So here we're taking root. Okay, we get sine of a equal to plus or minus the root of 225 is what? Is that 15? And the root of 289, 17. Okay? Yeah. So my question for you guys is, which of these solutions do I take? Do I take the plus or do I take the minus? Anybody? Yes, Thane, you take the minus because the angle A is in quadrant 3. Okay, that's why we need this information, right? Angle A is in quadrant 3. And in quadrant 3, sine all of them, right? Sine and cosine are both negative. Okay, so here sine is a negative. We are going to have to take the solution, take the negative solution. So sine of A is equal to negative 15 over 17, since A is in pi to 3 pi over 2. Okay, so that takes care of that. Now you're going to, yeah, so we just found, as I said, we have cosine of b already. We found sine of a. Okay, we have cosine a, we need sine of b. Okay, so let's do that quickly. Okay, so to find sine of b, again, we know that cosine square b plus sine square b is equal to 1. Okay, so plug in. We have cosine b again, negative 3/5. Okay, so square that plus sine square b, which is unknown, equal to 1. All right, so when you square 3/5, you're going to get 9/25. Move the 9/25 over. 1 minus 9/25 is 16/25. Therefore, sine square b is 16 over 25. We are going to take the root again. You get absolute value of sine b, or just sine b, equal to plus or minus 4/5. But again, b is, you're told that b is in quadrant 3, and in quadrant 3, sine is negative. Since b is in pi to 3 pi over 2. So when you move on to that higher math course, please make sure that you justify every step. If you really want to impress your professor, justify everything. Okay? Give great details of everything. That will earn you an A. I promise you. All right? Because if you justify, then you tend to remember why you're doing what you're doing later on. Okay? Now we go back to that expression. Okay, so we have, once again, sine of a plus b, which was sine a cosine b plus sine b cosine a. Plug in sine of a, we found that right here, negative 15 over 17. Use my handwriting here. Fix that. Negative 15 over 17. Cosine of b, we were given that already here. That is negative 3/5. Ooh, where are you going? There. Negative 3/5 plus sine of b. We also found that. Sine of b right here. Negative 4/5. And cosine of a, that was given already, negative 8/17. All right, and then you complete that. Yep. So just get the final answer. The final answer is going to be negative. Okay, it will be negative. So think about that. It is saying something about sine of a plus b. Okay, so if sine of an angle is negative, right, then that angle could be in quadrant 3, or it could be in quadrant 4. And waiting for that. Yes. The angle could be in one of
Excuse
those
me.
quadrants. Yeah.
You said it would be negative. I think with all the products
Oh,
it
no,
would
I'm sorry. It's
yeah.
positive. Yes, I apologize. This is positive. Right, right. This is definitely positive. Yeah, yeah, this is positive. So if sine of theta is positive, then theta is in either quadrant one or theta is in quadrant two. Okay? We don't know which of those is the case. Yeah. The question D is asking you where is A plus B? A plus B could be in those two quadrants. So when you answer question B, which is asking you to find cosine of A plus B, then you'll have enough information to know which quadrant this angle is in. Okay, so if you find cosine of A plus B and that is also positive, then you know for sure that A plus B is in quadrant two. If cosine of A plus B is negative, quadrant one, I meant to say, yes. So if cosine of A plus B is positive also, then you know that A plus B is in quadrant one. If it is negative, then you know it's in quadrant two. Okay, yeah. So do question B for yourself, please. B is the cosine of A plus B. And as you recall, the identity is cosine B minus sine A, sine B. And I already found everything. I've already found it all for you. Okay, so do that. And then for question C, do not please use an identity for that. Okay, question C is tangent of A plus B. You don't need a sum identity for that. This is just sine of A plus B, which we already have, over cosine of A plus B, which you already have. Okay? Yeah. And then, as I said, D, to answer D, just pay attention to the answer to A and B. Okay, so I thought problem two is pretty cool. Let's move on to the next problem. Yeah, so there is a thing about inverse functions. Problem three is asking you to find the sine inverse of negative half and so on. Yeah, so if you are told what is the sine inverse of, like, let's say root 2 over 2. Okay, so I'm just going to make something up here. I'm not going to do that question. So let's say you're asked to find sine inverse of root 2 over 2. Okay, so you ask yourself, hey, for which angle is sine root 2 over 2? And you may say, okay, well, sine is root 2 over 2 in quadrant 1 at pi over 4, also in quadrant 2 at 3 pi over 4. And you can also add 2 pi because the period of sine is 2 pi and get more answers, but that is invalid. Okay, if you're asked a question, there is only one answer to that question logically. If I ask you, hey, is this daytime? If you live in California, your answer can't be yes and no. It just doesn't make sense. If you're asked, what is 1 plus 1? Your answer is only 2. You can't tell me it's 2 and 0. It doesn't make sense, right? Because because we want sine inverse to be a function, okay? There is only one output per input of a function, else it doesn't logically make any sense. Okay, so there only has to be one answer to this question. So you ask yourself, instead of asking yourself, where is sine root 2 over 2? You ask yourself, in at what angle between negative pi over 2 to pi over 2 is sine root 2 over 2? Okay, the range of sine inverse is from negative pi over it's from negative pi over 2 to pi over 2. All right, this function has a limited range. Okay, so we ask it for what angle in negative pi over 2 to pi over 2 is sine equal 1. And oh, my screen froze here. Here it goes. That's what I was talking about. My screen freezes sometimes. Yep. So the only answer here is pi over 4. All right. Sine inverse of root 2 over 2 is pi over 4. Okay, so just a quick review of the domain for the domain and range of inverse strict functions that appear a lot in calculus 2. Okay, so let's go with f of x equal to sine inverse of x. Okay, this function has domain from -1 to 1. You are allowed to take value, x is allowed to be between those 2 points. Because if somebody asks you, what's the sine inverse of 1.5? You ask yourself, where is sine 1.5? Sine does not exceed 1. It doesn't go above 1. Just doesn't make any sense. So that is the domain of this function, and the range is from, as I said, negative pi over 2 to pi over 2. So range is the answer or the output of the inverse function. Okay. Um, let's say we have f of x equal to cosine inverse of x. Okay, so like the sine function, since cosine is bounded by -1 and 1, then cosine inverse takes in values that are also from -1 to 1. Okay, but the range of cosine inverse is from from 0 to pi. Okay, so let's actually graph that. Yeah, so the range of cosine from 0 to pi, it's allowed to be here. Okay, because why is that? Because this covers both positives and negatives for cosine. In quadrant 1, cosine positive. In quadrant 2, cosine is negative. So it covers both range of values. For sine inverse, as I said, from negative pi over 2 to pi over 2. Okay, and one of the most important inverse trig functions in calculus 2 or higher is the tangent inverse function, or arctan. Yeah, the domain of this function. So as I said, this function is so important because its domain is actually all reals. Right? Why is that? If you look at the graph of tangents, this is the graph of, let me do that again, a graph of tan x from negative pi over 2 to pi over 2. Okay, so not a great looking graph, but almost. Graph of tangent function from negative pi over 2 to pi over 2. The range of tangent is all real. So when you look at the inverse of it, it becomes the range becomes the domain of tan inverse. So domain is all reals, but the range is from negative pi over 2 to pi over 2. That's why this function is so important. You can input anything for tan inverse. Range from negative pi over 2, excluding those endpoints because tangent has an asymptote. Okay? Yeah, so when you're finding inverse trig values, keep those in mind. All right? I want to go over questions that are actually super important here. Question like 6. All right, so today we don't have that much time. I want to make sure you guys do actually understand or know how to do question 6 as well as question 9. All right. Um, you probably have not seen these questions a lot in pre-calculus. Yeah, but yeah, you know what? Let me actually do one more example here quickly. So let's say let's say I am to find cosine inverse of negative root 2 over 2. Yeah, just an example. So you ask yourself at which angle from 0 to pi is cosine negative root 2 over 2. Okay, so here's again the drawing that I have above for cosine inverse. Yeah, so this is the range of cosine, the range of cosine inverse. Okay, and we want cosine to be negative root 2 over 2. Well, in quadrant 1, cosine is positive, so you forget about that quadrant. That is not what we are looking at. In quadrant 2, cosine is negative, so that qualifies. So at what angle in quadrant 2 is cosine negative root 2 over 2? And I was expecting an answer from somebody by now. Anybody? You can open your microphone and tell me the answer. Anyone? We are off to a great start, aren't we? Don't be shy.
3 pi over 4.
Yes, thank you, Max. Thanks. Yeah, just you don't need to raise your hand. You don't need to. Or I'm not gonna be able to look at like 3 different screens. So first come, first answer. That's fine. Yeah. So Dane and Rosa, we typically wanna give the answer in radian form. I know sometimes the degree form is much better to comprehend, but spit out the answer in radian form. Get used to radians, giving the answer in radian. So yes, 3 pi over 4. And that is the answer to this. So that would be this angle here, the 45-degree from the positive y-axis. Okay, 3 pi over 4. All right, cool. Okay. Yeah, if you guys want to do problem D for for problem 3, you can just yeah, that's not a big deal. Just answer sine inverse of half, cosine inverse of 0, add them, and then find the sine of that for problem 3. So yes, I wanted to jump to problem 6. It's a type of interesting problem. Thank you, Mitch. Mitch is telling you how to convert from radian to degrees or vice versa. Okay, so problem 6 is asking you something like, what's the tangent of cosine inverse of x? Okay, and you're told that x is positive. Okay, x is restricted here. Whenever you're told that the quantity or the variable is positive or negative, then expect some sort of a square root, because square root of x squared, that is going to give you a plus or a minus. Okay, yeah, so let's understand something about inverse trig functions. Going back to the previous problem, when you are asked for cosine inverse of negative root 2 over 2, the answer is an angle. Okay? Sine inverse, cosine inverse gives you the angle. Again, cosine inverse of negative root 2 over 2. At what angle is cosine negative root 2 over 2? So an inverse trig function.
Professor, we can't see the paper.
According to Methway, the exact value.
My phone is going nuts. You can't see what?
We couldn't see it before. We can see it now.
You can see it now? Okay, cool. Yeah, so an inverse trig expression gives you an angle. Okay? Yeah, so note that an inverse trig expression, or an inverse trig term, outputs an angle. Okay, so what you do here is you're going to call cosine inverse x to be theta. Okay, let theta equal to cosine inverse of x. I'll make that green actually. Yeah. All right, so go back to the problem now. Use the substitution. So here, tangent of cosine inverse of x, or sometimes called arc cosine of x, simply becomes cosine of theta. Okay, so what you have to find here actually is cosine theta.
Professor,
Yes.
I have a quick question.
Go for it.
Why did you write cosine theta if we're letting theta be cosine inverse of x? Isn't it tangent theta? Or
Oh, thank you. Thank
Oh,
you for that.
sure, no problem.
Good catch. Who is oh, who was telling me that, making the comment? Ike, it was you?
Benedetta, just go by Benny.
Okay, thank you. All right, so yes, this is tangent of theta. That was fast catch, actually. Very good. Yeah, so tangent and cosine inverse x becomes tangent theta. Basically, what you're finding here is a simple trigonometric ratio. Okay, so let's see how to find tangent of theta. Going back to the relation between theta and x, right here. Okay, if theta is cosine inverse of x, so we're going to come back to this tangent theta. So if theta is cosine inverse of x, then we know that cosine of theta has to be x. Correct? Yeah, cosine theta has to be x. Because that is basically the inverse relation. Look, so you know that if like let's say A is equal to F inverse of B, then F of A has to equal to B, right? Because they switch their domain and range. Okay, so here theta is the range. Theta is the output of cosine inverse. So because the domain and range switch, then the output of cosine inverse becomes the input of cosine, right? And the input of cosine inverse, x is the input of cosine inverse. That input becomes the output of cosine function, basically the inverse relation. So here I have cosine of theta, and let me draw that theta actually in green. I have the cosine of theta. My goal is to find tangent of theta. You have cosine theta, you want to find tangent of theta. You can use a simple right triangle approach here if you want. You can also use the trig identities. So given, that's the goal. Goal, given cosine theta, which is equal to x, we want to find tan theta. Yeah, so cosine of theta here is equal to x. Well, cosine is a trigonometric ratio. It's a ratio of adjacent to hypotenuse. Think of x as x over 1. Okay, as I said, x becomes the adjacent, and 1 is the hypotenuse of a right triangle that you're going to draw for yourself here. Okay, whatever one of the legs is broken here. Yeah, so here is theta. Adjacent is x, hypotenuse is 1. And what you want to do is find the missing side. Why do I need to find the missing side? The missing side is needed because tangent theta happens to be opposite over adjacent. Okay? I need the opposite. I have the adjacent already. I need the opposite. So use a Pythagorean theorem. The opposite, this opposite here, is square root of 1 minus x squared. Okay, we all know that. You can find that quickly. Okay, so always find the missing side. Now go back to what you're trying to find. So here, the tangent of theta is equal to, as we said, opposite over adjacent. The opposite here is square root of 1 minus x squared, and the adjacent is x. All right, so as easy as that. So what did I want to find? I wanted to find tangent of cosine inverse of x. That's it. That's it. That's the tangent of theta. Right, so theta was this cosine inverse x. Yeah, so root 1 minus x squared over x. Okay? And you know, I'm gonna share these notes with you guys. Guys, at the end, you can use them. Okay, so that's that. And please try to do rest of problem 6 in your own groups. So always call the inverse part theta, always. And use the inverse relation in basic Pythagorean theorem here, okay? I want to go to also problem 8. I know I'm skipping problems in between. Those problems are basically just basic trigs. Okay, problem, what did I say? Problem 9. Yeah, like to do problem 9. Okay, because problem 9 is what you use in what we call trigonometric substitution in calculus 2. In calculus 2, as I said, one of the main objectives is to find antiderivatives. Okay, and if you have taken calculus 1, then you know how to use a simple or basic u substitution to find the antiderivative of certain composite functions. But in calculus 2, you're going to learn about trigonometric substitution when finding an antiderivative. All right, so if you look at problem 9, it says, make the appropriate trig substitution to obtain a simplified trig expression that contains no radical or absolute values. Let's see what they're talking about here. Okay, so I'm going to do an example here, and then I'm going to write out the rules that you need to kind of attack these problems. All right, so let's look at problem B. Yes, so for problem 9b, we are given an algebraic expression. Right? What is an algebraic expression? An algebraic expression is an expression whose terms can be written as powers of x, okay? Like a polynomial or a rational function or a root function. So you have powers of x, like x squared, as I said, or a square root of x, or the square root of 1 plus x. So we have this, again, algebraic expression, x squared over the root of 9 minus x squared. Okay? Yeah. Let's go back quickly to the most important trig identity. that I already wrote down. Okay, so again, consider cosine squared theta plus sine squared theta equal to 1. Okay? Yeah. So let me do this. Let me move one of these terms over, either sine square or cosine square. Okay, so let me take sine squared theta over to the other side. Okay, so I'm going to get cosine squared theta equal to 1 minus sine squared theta. Right. Now, oh, my screen is lagging a little bit. Okay, so that's what we have so far. Now, let's multiply this equation by 9. Okay? You could do that. You could just take the Pythagorean identity multiplied by any non-zero value. So multiply by 9 to get 9 cosine squared theta equal to 9 minus 9 sine squared theta. I'm going to be telling you why I'm doing all this. Okay? I'm not expecting you to look at that problem and do all this. I'm just trying to show you why I am doing all this. There is a point to be made. Okay, so just pay attention to this identity here for a second. So here I have 9 cosine squared theta equal to 9 minus that 9 sine squared theta. Let me write it like this. Let's write it as 3 sine theta squared. Oops, 3 sine theta, then squared. Okay. So here it goes. Imagine, you guys imagine that I go back to this expression. Let's go back to this expression. Imagine that you are going to replace this x with 3 sine theta. Okay, so let me make that x blue. So again, this x is replaced by this 3 sine theta. Then this 9 minus x squared becomes, of course, this 9 minus 3 sine squared theta, which if you go backward, it becomes 9 cosine squared theta. So after substituting 3 sine theta for x, we get, of course, this, and we end up with just 9 cosine squared theta. And the square root of that is, if you take theta in quadrant 1 or quadrant 1, the square root of that is just going to give you 9, give you 3 cosine theta. So you go from the square root of the difference of 2 terms to a single trigonometric term. Something that looks pretty complicated algebraically to something that consists of only one term, one trigonometric term. Okay, so you see what's happening here? Well, let's do that. Let's do that. So, yeah. Substitute x to be 3 cosine theta. Okay? And assuming that theta is in quadrant It could be in quadrant actually, quadrant 4 or 1, but for convenience, take it in quadrant 1. Okay? Yeah, so let's do that substitution and see what happens. Okay, so I have here x squared over the root of 9 minus x squared. Let's substitute that. We're going to get, again, x here is, I'm sorry guys, I meant to say x here is 3 sine theta. Yes, 3 sine theta. So we get x is 3 sine theta squared over the root of 9 minus, again, 3 sine theta squared. Okay, so the numerator here is just 9 sine squared theta. And we saw what happened to the argument of the root. Okay? Yeah, so this 9 minus 3 sine squared theta is nothing but 9 cosine squared theta. I mean, you could see that. Let me just do it just step by step. So you have 9 minus 9 sine squared theta. Okay, you can factor that 9 out if you want. Let me just do it down here. Yeah, and you get, so this whole thing is just 9 cosine squared theta by the Pythagorean trig identity. And simplify, you get 9 sine squared theta on the top. In the denominator, we get 3 cosine theta. Well, that's, as I said, that's plus or minus. Square root of cosine squared theta is absolute value of cosine theta. It's plus or minus cosine theta. But the justification is that theta is in quadrant 1. I took it in quadrant 1. So you take the positive. So what's going to happen here if you simplify? If you simplify this, you get, well, I get 9 over 3, which is 3. You can write that as, if you want, sine theta over cosine theta times sine theta, right? Sine squared theta is sine theta times sine theta. You know, you can write it that way, which becomes 3 tangent theta sine theta. Okay, that's the answer. Yeah, you think, oh, well, you think we are crazy for doing all this, but no. Imagine somebody asks you to integrate this function. Okay? Yeah. The integral of x squared over root 9 minus x squared is not easy at all. It's not. You can't do that by just looking at it. Okay? But when you do this substitution, you end up with, well, you have a dx here. You know, this is calculus 2 stuff. You have to also change dx to d theta, but don't worry about that. The integrand becomes something that is a lot easier to deal with. This is much easier than that to look at in terms of integration. All right, so let me give you guys the rules of substitution. Okay, and yeah, we have the difference of squares and we have the sum of squares. So let's say, yeah, the rules. Let's say that you look at an algebraic expression like problem, if you have the worksheet in front of you, number 9, like problem A, problem B, yeah, A and B. It's a difference of 2 squares. So if you have, if the expression involves an a square minus x square, yeah, just like problem 9 and 9a and b. Okay, problem 9 is 25 minus x squared. Problem B, as I did, has 9 minus x squared. Then the substitution is this. Then you're going to let x equal to a sine theta. You can also make it a cosine theta, but a sine theta is easier. All right? Yeah. Again, because when you do a squared minus x squared, you get something easier. Okay? So do that. For something like question 9C and E, you have the sum of 2 squares. Yeah. If you have a squared plus x squared, a is a constant, like 9 plus x squared, then the substitution is this. X equal to a tangent theta. Here is y. So I did a square minus x square example for you. Here is y. Because in this case, a squared plus x squared becomes a squared, which is constant, plus x here is a tangent theta. We square that. Okay, you have a squared plus a squared tangent theta. You can factor a squared out. You have a squared times 1 plus tangent squared theta. And we all know that 1 plus tangent squared theta is another form of the Pythagorean identity. That is secant squared theta. 1 plus tangent squared theta is secant squared theta. So you have a squared secant squared theta. So what is the advantage here? You have 2 algebraic terms. A squared plus x squared is 2 terms. Here you have 1 term. You have a single trigonometric term. The number of terms shrunk down to 1, which is a lot easier to deal with, especially if there is a square root, okay? Algebraically very difficult. Here you have a single trigonometric term, a lot easier to deal with. Okay, yeah. So third case, like problem 9D and 9F, as well as G, if you have an expression and it involves x squared minus a squared. Here you also have the difference of 2 squares. The difference between these two is that one is the negative of the other. Here the constant comes first, and then the variable. Here you have the variable square minus the constant. They are the opposite. They're the opposite of each other. So if you have this, then the substitution you're going to use let x be a secant theta, and let's see why. So this is because x squared minus a squared becomes a secant theta squared minus a squared. Again, here you can take out the a squared, you get secant squared theta minus 1. And if you again recall, secant squared theta minus 1 is tangent squared theta. You get a squared tangent squared theta, which is again a lot easier to deal with. Let me do an example, one more example here quickly. So let's say I have x over square root of x squared minus 7. All right. Yeah, here you have a difference of two squares, x squared minus a squared. So it's the secant substitution. First of all, recognize your a. Here a squared is equal to 7. Right, this number is what we call a squared, 7. So your a is root 7. Okay, a is a positive constant. A is always positive. Therefore, you're going to let x equal to root 7 secant theta. Okay, that is the substitution rule. Okay, we're dealing with this case. It's a secant theta. Plug in x is root 7 secant theta. That is going into x. Everywhere you see x. All right, and then start simplifying. And again, I'm taking all my angles in quadrant 1. You could just take that substitution. So within the square root, you have square root of square of root 7, 7 secant square theta minus 7. Okay, now within the square root right here, if you were to factor the 7 out, you get secant square theta minus 1, which is tangent square theta. So here you have 7 times tangent square theta square rooted. Okay, take the square root of 7 tangent squared, and that gives you, again, 1 more root 7 tangent theta. Again, the square root of tangent squared theta is absolute value of tangent theta, but theta is in quadrant 1. So in quadrant 1, tangent is positive. Root 7's cancel out. You can simplify this using, I don't know, the identities. Secant is 1 over cosine theta. Okay, 1 over tangent theta is cosine theta over sine theta. Yeah, 1 over tangent theta is cotangent theta, cosine over sine. These cancel, and you end up with 1 over sine theta. 1 over sine theta is just cosecant theta. So look at how significantly the original algebraic expression reduced to. Okay, look at that. This crazy looking algebraic expression versus just a single trigonometric term. All right, that is a tremendous amount of simplification. Imagine if you're asked to integrate that. You could use a substitution, but the integrand turns into something much simpler that you can handle. Okay? Yeah. So I'm gonna put you guys in groups. I'll do breakout rooms. I think I'm supposed to give a little bit of a break. So please take like a 10-minute break while I'll do the grouping, and then we'll continue. Okay? So when you come back, you're gonna be in your own groups. All right? So please take a 10-minute break now. If you have a question, let me know through the chat box.